So we left off on a cliffhanger that we needed a new thermodynamic variable. And so now we're going to introduce a new thermodynamic variable called entropy. So entropy has the symbol of capital S, and the units associated with entropy are temperature or energy per temperature, so joules per Kelvin. You can also get joules per Kelvin per mole, so joules per mole Kelvin, similar to the fact that enthalpy is usually joules or kilojoules, and then you can have kilojoules per mole. So it's going to be the same idea we could associate with that, but joules per Kelvin is our entropy units. And the purpose of entropy is to quantify disorder. Okay, so quantify the disorder in a system. And so we're going to spend some time talking about what exactly that means. And so when we talk about systems that are disordered, in a lot of ways, we can just kind of look at two examples and kind of you have an inherent understanding of entropy. So something that is ordered would look like, say, this. Right? That would be a low entropy system. You have your circles and they are in a pattern that repeats itself, right? They are in an arrangement where they're all following a pattern. This is the same number of circles, but they're arranged seemingly randomly, right? And that is what we mean by disordered. And so the goal of entropy is to quantify, assign a number to how disordered are these systems. And so we would say that, you know, the one on the left with where the dots or the circles are in a nice pattern has a very low entropy, whereas the one on the right where the dots are just kind of randomly jumbled together would have a high entropy, or at least certainly higher than the one on the left. One of the ways that we can go about quantifying disorder, assigning a number, is thinking about the number of unique arrangements that are possible for a system or for some sort of group of objects based on specifications as to how you make that system. So you can quantify the entropy of anything. So let's think about the ways that we could put 8 students in 25 desks. So we're going to put students in a classroom. And when we talk about the entropy of it, then it would be what is the disorder of those arrangements? And so we could set up kind of like a recipe for how we're going to make it. We could have the first prospect could be the students fill each row from the front of each row from the front of the room in alphabetical order. Okay, so we're going to put them in alphabetical order. And then the second option would be the students randomly select seats. So, you know, we can probably already see, make some predictions which one's going to be more disordered. But, you know, these are kind of the specifications. We want to quantify the number of unique arrangements that we would have for those two kind of recipes. So when you say they're going to go from the front row and they're going to go in alphabetical order, there's only one way that happens. Right? There is only one way that you start with the first alphabetically, A, B, C, D, you know, so on and so on. And so that's a very ordered system because there's only one arrangement. Okay? It's not necessarily ordered because the students are all in the front, but because there's only one way that system can look. So the system being the collection of students in desks. So there's only one way that they could be arranged. And any time we only have one possibility, that would be a very ordered system and therefore have a low entropy. If we allow students to randomly choose seats, there's a lot of kind of possibilities. And so we would look at something like this and think that's pretty disordered. But the problem is not that the people are randomly arranged, but the fact that our parameters for how we assigned people to seats is that they could go wherever they wanted. Meaning there's a lot of possibilities, right? Some of those possibilities will have order, right? They'll be a nice little pattern, but you could still have all these different ways. If they randomly arrange themselves, it may look like it's an ordered position, but the important thing is the reason why the system has entropy is not that the people are randomly arranged, but because there's a lot of ways for those random arrangements to exist. There's a lot of possibilities, a lot of unique ways that system can look that has a very high entropy. So we know that these systems with low entropy, there are fewer possible arrangements. So if you say everyone's going to be in a ring, or everyone's going to sit in the back of a class, or everyone's going to sit in the front, there's only one possible arrangement, which means the system is more predictable. So when we talk about being ordered, there is very low numbers of arrangements. The system is very predictable. We know exactly what it's going to look like. We know exactly where I could find my students. So if we think of, say you have 5 pots. So if I put all the pots away in the cabinet, it's relatively easy to find a particular pot because you only need to look in the cabinet. That is an ordered system, right? You put things away. You inherently know that that is how you order, say, your house, but it also makes it more predictable. Think about it if you didn't have a specified pot cabinet and instead you just had your pots strewn about your entire house. It would be very hard to find a particular pot, especially if you have 5 of them, because now it's not only I need to find any pot, but I need to find a particular one. And it could be anywhere in your house. You have more places to look. You could, find your skillet when you need your stew pot, right? And that's a problem, right? That makes it more disordered and less predictable, right? The less predictable it is, the more disorder there is inherently in the system. So high entropy systems have a lot of disorder, many arrangements, and low predictability. So if you leave your kitchen super messy, that's a lot of disorder. You can look at that and inherently know that that's disorder. So the idea of entropy is how do we quantify just how disordered it is? And things that are highly disordered, there's many arrangement. There's just piles of trash on these counters. There's a lot of different ways you can pile trash on a counter, right? There's all sorts of different ways. It could be all over the place. I did note that this area of the floor is not full. You could put stuff there. These cabinets don't have anything in them yet. Stuff could go in there. What goes into this meager trash bag? What gets put in the corner? What gets put on top of the oven? What goes over here? What goes over there, right? You could move the garbage around and you still have a disordered system. You still have all the garbage strewn about. It's very low predictability. If you want to find a particular piece of garbage, that's going to be hard. You're going to have to comb through every single bit of it, right? There are pots and pans in here. You got this thing up here. You got some other ones kind of poking out around, stuff over here. It's going to be really hard to find anything. Say like you got some coffee somewhere in here. Good luck getting it. You're going to have to go through every single piece of garbage in order to find it. Lower entropy, say you hang your pots up in your kitchen. If you need to find a pot, you would need to potentially look. There are some variability of arrangements. What hook exactly is it on? But you only have 1, 2, 3, 4, 5, 6, 7, 8, 9 places to look. You can count explicitly the number of places to look. That means it's more predictable. It has fewer arrangements. That is more ordered and has a lower entropy. So you inherently kind of are familiar with what order and disorder means, and entropy is just kind of a way for us to quantify that, to assign a number. This system has, double the entropy, means it has double the disorder, and it's all about counting arrangements. The book goes really hard into counting arrangements. We just want to know that it is more arrangements. The more kind of arrangements and variety you could have, the more entropy and lower predictability. Both of those things help us quantify disorder and therefore give us a value for entropy. All right, another video down. No participation questions in this one, but plenty more videos to go. See you in the next one.